If you're up to date on my videos, you'll know that one item on my to-do list is to build a clock for my relay computer. Now I could just build it and pop a summary video on YouTube, but that would be way too easy. So instead I've decided to put together a mini-series where I'll try and explain what the clock does and then design and build it before your very eyes, from prototype all the way through to final working PCB. So let's start at the beginning. What is a clock and why does my relay computer need one? Well, in computer terms, a clock produces a steady rhythmic signal that goes on and off. If you were to draw it out, it would look something like this. Here we have a time increasing towards the right and voltage increasing towards the top, and you can see how the signal flips between a higher and lower voltage state over time in a nice steady repeatable pattern. This is also known as a square wave because, well, I'm sure you can work that out for yourselves. We'll take a closer look at this clock signal in a moment, but first, why does my relay computer need a clock signal at all? The whole point of a computer is to take a list of instructions, a computer program, and follow them in an order to perform some useful function. Although the computer might need some input from me at the start, or maybe at some point later in the program, it should otherwise just get on with it. Let's take a simplified example to see what's involved. Here we've got a two-line program that copies a value from register B into C and then copies register A into B. Not particularly useful, but the computer isn't fussy, it will follow our instructions to the letter. Both lines are the same class of instruction but have slightly different parameters for the source and destination registers. Here's a diagram of what we're asking the computer to do. Copy B into C and copy A into B. So, we've told the computer what we want it to do, but how should it approach the problem? How, and more importantly when, to copy the value? Well, the computer has a timing chart built in for each class of instruction that tells it what to do and when in order to execute the instruction. Here's a timing chart for move. This tells the computer that it needs to select the source register onto the data bus, and whilst it's doing that, load the destination register from the bus at the same time. Obvious, yeah? Well, not quite. It needs to let go of the register load line before letting go of the select line, because if they came off at the same time, there's a risk that the value disappears from the data bus slightly before the destination register is finished using it. Effectively, that would just cause the register to store the 0 value now present on the data bus rather than the intended value. The timing chart therefore leaves a nice gap to let the value stabilise on the bus and then leave it hanging around well beyond the point the load line is dropped. So the computer knows what to do, when to do it, and relatively speaking, how long to do it for. Easy, yeah? No. So where does the computer get these pulses from, and what makes the top one last twice as long as the bottom one? Well, this is where the sequencer comes in. It produces a selection of the common pulse shapes that can be combined into operations like the one here. Here's an example of those pulses. In the case of the move instruction, it's using pulses C and D. You can also see pulses A, B and E, and of course there's plenty more pulses available, a total of 19 in fact, that can be combined together to perform other instructions. So, I guess you're thinking, that's all fine, but how does the sequencer produce these pulse shapes, and will all this madness ever end? The answers to which are finite state machine and no, this madness will never end. In the simplest terms, the finite state machine's job is to count. Its outputs look like this. Now this might look a bit confusing, but effectively it'll produce numbered pulses in a set order. Pulse 1, then 2, then 3 and so on. Effectively it's counting up. The S-dash pulses come on one after another, whereas the non-dash pulses last twice as long and overlap. If you compare the state machine diagram on the left with the sequence pulses on the right, you can see pulses are simply made up from state machine outputs. In our simple case of the move instruction, pulse C is taken directly from S5 and pulse D from S5 dash. Pulse E is one that combines outputs S4 and 5 in this case to make a longer pulse. Depending on the complexity and execution length of the instruction, the state machine will reset its count to 0 after 8, 10, 12 or 14 counts, or if it's a really complex instruction, it'll count all the way to 24. In the case of a move, it's a nice simple 8 count instruction. So, what's driving the finite state machine? What exactly is it counting? It's the clock, of course. That steady beat gives the finite state machine something to count. The clock literally is the beating heart of the computer. So, just to wrap this chapter of the video up, here's something that will make your eyes water. Here's the full state machine timing diagram showing pulses 1 through 23, and right there at the top in red is the clock signal driving the whole thing. So to recap, the clock drives a finite state machine, which drives a sequencer that derives a family of pulses, which are used by the controller to operate the right control lines at the right time, in order to execute an instruction as part of a larger program so that the computer can do something useful for its human overlord. Keeping up? Okay, I'm being a bit tongue-in-cheek here of course, but you can hopefully get a feel for just how combining lots of simple things together can make something much more complex. But none of it's possible without that clock signal. So let's take it down a peg and get back to that nice rhythmic beat of a square wave. And let's look at some of the characteristics of the clock signal and introduce some terminology. Firstly, we can see that the signal is made up of highs and lows. We can also describe these as peaks and troughs, or positive and negative halves. The pulse width defines how long each peak lasts for, and each pairing of a peak and trough form a single cycle or period. Each cycle is repeated, and on screen right now we can count 8 cycles in this signal. The distance between the peak and the trough is the amplitude, and in this case this will be measured in volts as that's what's being manipulated by the clock. In reality this signal could be modelling anything though. It could be the height of a flag being raised and lowered over a week, for example. At the point the signal drops from high to low, we call the falling edge, and likewise when it goes low to high, we call that the rising edge. In this computer, things happen on both the falling and rising edges of the clock signal. Note also here that the peaks and troughs are equally sized, so in each cycle we spend 50% of the time in the on state and 50% in the off. This ratio is known as the duty cycle, and here it is 50%. Other options are available of course, and if we were on for 75% of the cycle and off for 25%, then our duty cycle will be 75%. Here though we want a nice even clock signal with a duty cycle of 50%. Although depending on what tech we use to implement the clock, getting exactly 50% might not be quite possible, but we should be able to get close. So we now know a bit more about our clock signal, but it's all a bit relative at the moment. We don't have anything to measure it against. Let's make it specific. The easiest thing to go for first is the amplitude of the signal. That literally just needs to replicate flicking the power on and off. So we peak at 12 volts and we trough at 0. In fact, if you operate the clock manually on the computer, that's exactly what's happening. You're flicking the power on and off on the clock line. The time factor is a bit more interesting as that will have a direct impact on how quick the computer operates. We want to strike a balance here where it's going quick enough to get stuff done in reasonable time, but also not so quick that it's just a blur for anybody observing the computer running. Plus we could go so fast that we exceed the speed the relays can actually operate at. And how do we define the speed of a computer anyway? Well, it's based on the clock signal of course, and it's measured in number of cycles per second. One cycle is 1 Hertz, so if we take a time period of 1 second, and in that period we have 4 cycles, then that's a 4 Hertz clock signal. Because the computer operates on both the leading and falling edge of the clock signal, then a 4 Hz signal means the computer could do anything up to 8 operations per second. An 8 Hz signal would take that to 16 operations per second, and so on. So we've got our amplitude of 12 volts and we've got our frequency of 6 Hz. Ergo, we've got our target clock signal. At 6 Hz, each cycle lasts just under 167 milliseconds and we have a pulse width of 83 milliseconds. What's next then? Well, we now need to decide how we're going to generate this clock signal, but that's something for the next episode in this series.